In the previous video, we elaborated on the crystalline silicon and perovskite hybrid tandem devices. Although this seems a promising hybrid technology, there are also other suitable top cell candidates such as the III-V materials. Therefore, in this video we will discuss the combination of III-V semiconductor materials with the crystalline silicon. More specifically, we will discuss the motivation for combining crystalline silicon technology with III-V materials. This is followed by the reviewing the state of the art and comparing this with the potential of this hybrid technology. As explained in the previous video, the motivation for combining crystalline silicon into a tandem device is to further enhance the efficiency, since crystalline silicon is reaching its single junction limit. We have also seen that the ideal band gap for the top cell in the combination with a crystalline silicon bottom cell is 1.7 electron volt in a two-terminal device, resulting in an efficiency limit of about 43%. Furthermore, a four-terminal structure enables a larger variety in the band gap, while still having the same high efficiency limit. Let us now apply this knowledge on the band gap versus lattice constant charge, which we have seen before when we discussed the III-V semiconductor materials. In this case of a monolithic integrated two-terminal tandem device, it is preferable to have lattice-matched materials. In the diagram we can see that there is no III-V material present with the same lattice constant as the silicon that exhibits a band gap of 1.7 electron volts. However, if we consider a four-terminal structure of the device, lattice matching is not an issue. We can see that it is possible to mix gallium, arsenide, phosphor and indium and aluminium and obtain a band gap that lies within the ideal range. One might recall that the III-V semiconductor materials are relatively expensive compared to the other PV technologies, since the elements are not very abundant and the processing methods are relatively expensive. This is in contrast with, for example, the perovskite, which we discussed in the last video. So why are we interested in a III-V crystalline silicon tandem device? The III-V technology has reached the highest conversion efficiency to date. The performance does not degrade over time and the material is stable. Put differently, the technology is already quite mature, especially compared to perovskites. Consequently, with the current state-of-the-art technologies, the maximum possible efficiency for the III-V crystalline silicon four-terminal tandem device is as high as 35.5%. We will now see how this compares to the actual achieved maximum efficiency up to date. The record device consists of a four-terminal mechanically stacked structure. The top cell, from which we can see a simplified version, is based on a gallium-indium phosphide cell with a near-ideal band gap of 1.8 electron volt. The record efficiency obtained with the cell in a single junction device is 21.4%. For the bottom cell, a HIT structure is chosen which exhibits a single junction efficiency of approximately 22%. These two cells were attached to a glass slide by an epoxy adhesive. The resulting device exhibits a record efficiency of 32.5%. Alternatively, by using gallium arsenide as the top cell, a record efficiency of 30.8% has been reported. Nevertheless, this record efficiency surpasses the maximum theoretical efficiency of 29.4% for a crystalline silicon single junction. It also exceeds the record single junction efficiency of 28.8%, which has been demonstrated by a gallium arsenide single junction device. The latest record efficiency has even outperformed the previous dual junction tandem device record, which was based on a two-terminal all III-V structure with an efficiency of 32.6%. It is also possible to grow III-V directly on crystalline silicon by epitaxial growth. However, the lattice mismatch and the large difference in thermal expansion coefficient impose a serious challenge. Therefore, the efficiency of such tandem device has been limited to 21.4% so far. Wafer bonding is another two-terminal production mechanism. In this process, the top and bottom cell are fabricated separately and thereafter bonded together. The record device was able to reach an efficiency of 25.2% up to date. However, this approach demands very clean and low roughness interfaces for bonding. In summary, we have applied the knowledge of the optimal top cell band gap on the III-V materials. We have discussed the motivation for combining III-V semiconductor materials with crystalline silicon. Since the III-V technology is relatively mature, the maximum crystalline silicon and III-V tandem efficiency should be able to reach efficiency as high as 35% based on the current technology. The 4-terminal device strategy results in the highest demonstrated efficiencies of up to 32.8%. These efficiencies are much higher than the ones achieved for the 2-terminal devices, since these face challenges regarding lattice mismatch and difference in thermal expansion coefficient. In the following video, we will discuss another hybrid device combining organic PV with thin film silicon.